Welcome back, physicists. You all just demonstrated that you know how to open a door. Anybody have a good explanation for why it's so hard to open the door when you're on the wrong side? That's okay. Intuitively you know that it's challenging. You can physically feel how much harder it is when you try to open a door on the side that the hinge is on. But yo,
When you're moving on the handle side, you use less force because it's over a greater distance.
ooh, the distance you are away from your axis of revolution, or the hinge in this case, certainly plays a role in this. Now, beyond that, there are some other little pieces. If I say the word dynamic, do you remember what it means? Moving. So, in 8.2, where we're jumping in today, and we're going to get the first part of it, 8.2, our focus is on rotational dynamics. So, the movement of rotation. Cool. Now, when we're looking at rotational dynamics, there's only a few basic ideas that we're going to see today, and one of them we really just got. As I open a door, if I were to trace the path that door makes, do y'all agree it's a circle? So I must be working somewhere with angular acceleration, angular velocity, all that stuff. And Sean, I heard you trying to make the connection between linear velocity and angular velocity. Love it. That's exactly what I was hoping to hear here. Now, at its most basic, I'm going to front load this just a skosh. I can apply a force on something to make it move. We all know that's true. That's what a force is. If I push more than whatever force is resisting, it moves. Now, there's a difference in movement in a linear sense and a rotational sense, but they can be treated essentially the same, just with different formula. We know that force makes stuff move in a straight direction. Turns out we still need force to make stuff move in a circular fashion, but instead of just calling it force, we're going to say torque. Torque causes, and I'm going to write down just this guy. And what did I just write? Torque causes what? It is alpha, but I don't, that's fine that we know the letter and good, but what is this? Louder? Angular acceleration. This is like the big takeaway from this lesson, just so you know. We just said, here it is right off the bat. Now, looking at this, immediately our first section then is we need a way to relate this idea of force and torque together. So we're going to look at force and angular velocity, because they must be related to each other. Now, I'm about to draw a terrible door, just for the record. It's not going to be good. If I want to push the door open easily, you guys said push near the handle, as far away from the hinge as I could. And then there were some other obnoxious things that I wanted us to do. If I'm looking at a door, and we'll say here's a hinge, and then here's a lovely door, and this is the end of the door. If I want to push and open it here, I need a ton of force to do this. If I say, here's the force that I need, and you guys saw this, it takes a lot of energy to push it if you get really close to the hinge. Now, in contrast, it'd be much easier to push out here, right? Now, if I try to push at this angle, like this, is it going to work very well? Even, my hand will probably slide on a door realistically, but even if there were friction, there's a lot of wasted energy going into this push. You guys identified correctly that this is not any good, but there's a better way to do it. How should I push on the door? Perpendicularly. So this is the easiest. And I'm going to show with the arrows that, hey, look, this is optimal. Now, when we're looking at this, we want to push perpendicular to the door about our axis of revolution. So we're going to sneak a few vocab in here. In our sense of a door that's on a hinge, there's lots of stuff that spins that doesn't have the exact same hinge mechanism, but we have a shorthand that we're going to use. We have an axis of revolution, and I'm going to write this one time, axis of revolution, which is where we spin about. And I don't know why the font is coming out so ugly. Which I would like to never have to write axis of revolution again. Any suggestions? Or thoughts on what I might use? AOR, and I'm just going to specify so that AOR, the axis of revolution. Now, in the case of a door, what's the axis of revolution? It's the hinge. What about our planet? Our planet spins. Where's our axis of revolution? Say it again. So it's kind of like the core, but we have to imagine there's a vertical line running through it, right? Like straight along our magnetic field, north and south, where we rotate. Okay, as we look at this, there's nothing crazy here, I don't think. It is easiest perpendicular, the furthest possible distance away. Now, the idea that we're seeing here is actually a simple machine. And when we look at simple machines, there's several of them, but the easiest one that, in my mind anyway, is the lever, or the lever arm specifically. So we're going to define this real quick, the lever arm, which henceforth, this is simply a capital L. Now, when we look at our lever arm, there's a few things that get weird with it. I'm going to take the time to actually draw like a wrench so we can see it out specifically. But we're going to say that the lever arm, by definition, and we'll draw it to make sense of it, is simply the perpendicular distance from our axis of revolution, or AOR, the hinge on our door, if you will, to the point where force is applied. To the point, and I'm going to say, yeah, we're fine with that, the point where force is applied. Now, as we go through these lever arms, there are some weird things occasionally. The first little comment, I'm just going to say theta matters. And without going any further, when I say theta matters, what am I referring to? The angle, what angle? Talk it out. I'm okay with the answers are wrong. We care about the angle at which something is done to the door. And I showed you guys the silly way to open a door that didn't work very well. If I want to spin this around where I'm holding on my hand, is this a good angle to push at? No, the angle that we push at should probably be up here, and I'm measuring more perpendicular up here, right? Whatever I'm trying to turn. Now, to make this as nice and easy to make sense of as we can, I'm going to use some video editing. We're going to make a small wrench. So, here's my wrench with a force applied. Sorry, I forgot to resume it. I want to be able to identify all of these different pieces. Now, when we look at this situation, this very specific reference, not reference frame, I'm sorry. Oh my gosh. System. Was that you that saved me just now? Somebody over there, I thought, whispered it. Check it out. What do you think we should call this distance? What do we normally call the distance from something to something else? And let me rephrase this. If I were to spin this, the whole wrench is going to move in a what? It's a circle, so this is my radius of that circle, because everything is revolving about this. So we're going to use radius r. Now, here's the part that can get kind of weird sometimes. If I look at this, the distance from the axis of revolution to the point where the force is applied, we are tempted and probably reasonably want to call this radius my lever arm. However, when we're applying our force, it's a strange little connection because my force physically touches here, but I apply the force over here. Do you guys agree with that? Like, I'm actually adding the force from this point. Now, if I wanted to go from my axis of revolution and be perpendicular, if I just draw out a line right now, it's pretty close. If it weren't close, could I extend this force out further? And by that, I mean, and you don't have to change yours, but if I had just a little tiny force right now, I don't think that I can get a nice perpendicular angle here. Not quite anyway, right? So could we conceivably extend that out just a skosh just to see it as a perpendicular? I'm just extending one side of my triangle to make this a right angle for me. Now, this distance that is perpendicular to my applied force and the point where I'm actually applying that force from the axis of revolution has a specific name. What do we call this distance? From the axis to the point wherever I'm applying force. So I'm okay with you say opposite because you're thinking trig stuff, I imagine. We're going to identify this as my lever arm. Now, there's only one more little piece that we need to add in here. We got the lever arm L, we have our radius, the length of whatever it is that we're turning, and then we have our force, and I'll put the F back on there. Man, there's an angle in here somewhere. This angle right here is our theta. And this is the one that we looked at over with the doors as we were opening them. I want that theta to be perpendicular if at all possible. Now, all of these ideas come back in, but what sort of triangle do we have here? I have a right triangle. And from this angle theta, there's a few different things that I know. Now, my force might vary, but I don't think that my radius will ever vary on a wrench, and I don't think the lever arm will truly vary either except this angle. As we're looking, could you write me an expression for the sine of theta? And let me rephrase that. Write me an expression for the sine of theta based on this picture. What's that Lakota chief that we're going to use? SOHCAHTOA. So is what we're looking at. What's the opposite from angle theta? L, or the lever arm, over what's the hypotenuse of this triangle? The radius r. Now, if we're looking for a lever arm, it seems reasonable that maybe we don't want to have to do this trig every single time. We just want a shortcut. Could we solve this for L? I think so. One step away. We determined that L is equal to r times the sine of theta. The length of my lever arm is entirely determined by the radius of whatever we're working with and the angle at which we're pushing on it. This idea is an important one. I believe that this idea is one that does not show up on your cheat sheets. Can somebody confirm that? L equals r sine theta probably does not show up. Now, there's a little bit of gray area because maybe it does and we just didn't write it. But we're going to keep kicking on. Before going, any part of this that you don't feel okay with? Cool. Now, as I look at this, this is the word for word, the book. I don't know that I love it. I kind of just want to say perpendicular to the force and stop there because this misleads me. But with the picture, I think we can sort it out. If you wanted to make a change, I'm okay with not erasing, but just saying, let's think of it as perpendicular to the force so we can keep it straight. Now, looking at this idea, we are like 80% of the way where we need to be. The last little piece, once we have this, what do we say at the very beginning of the lesson causes change in angular acceleration? Very top thing, the first thing that I wrote today. I don't know if you guys wrote it. Torque. Okay. How many of you guys have heard the word torque? Not twerk, but torque. Okay, so if you are a car person, you probably have, because if you need to tighten bolts on a tire or something and you don't want to over tighten them and break it so that your tires fly off going down the road, you're going to use a tire wrench. Or if you're on a big fancy device, you're going to use what's called a torque wrench so that you don't over tighten and you don't under tighten it. There are super fancy wrenches that are designed to make sure that you don't apply too much force or too much torque while you're tightening a bolt. As we look at this, the big idea of this lesson is this idea of torque. Now, that's going to drive me crazy. I'm going to make it all caps. Torque. Now, we get a new Greek letter today. For torque, we will always represent it using this lovely Greek letter. Looks like a dumb T, kind of. Anybody know this letter? This is tau. Okay, torque, we will use the letter tau. Now, for definition, the wordy part of it, I don't know that we really need to write it down. What I care about is truly just the equation for this. I will make a nice definition. We'll think of this like force for circular motion. Or angular motion, rather. Now, torque is what is responsible for causing things to rotate. And if I want to open a door faster over here or easier, there's a couple things that I can do. I can just push harder. That'll open the door faster. But I can also make the angle better. If I push a certain strength at a goofy angle, that's possibly going to be the same as pushing perpendicularly with a way smaller force. As we look at it, here is the main part of this. Torque. Turns out it is exactly equal to F, the force that we apply, times R sine theta. Now, I made a comment a moment ago that you did not have lever arm written anywhere on your page. However, if you look right above what we just wrote, what do we define the lever arm L as? Hey, check it out. It really is here. This is the lever arm L. Now, in this situation, let's think about the units that are going to spit out here real quick. And I'm going to try to do a better job of making ugly notation, but to be helpful. What's force measured in? Newtons. So that's newtons, N, times, what is, sine theta is not measured in anything, right? Because it's going to be in radians. It's not going to be anything for me. What about R? Meters. What does it seem that the unit is going to be for torque? Newton meters. Huggins, you're kind of into car stuff. Have you ever used a torque wrench?
No, but I know what you're talking
Okay, so in a U.S. system, and really anywhere that I've ever seen, I've never worked on anything in a different country.
about. You get like a juice bag.
Yep, if you get torque wrench out of the shop over there, you're going to be able to set it to a certain amount of foot-pounds, which is a very different feeling. But check this out. A foot is a measure of what? Distance, just like meter is. And a pound is a measure of force, just like newtons. Hey, look at that. Newton meters and foot pounds are similar ideas. Okay, we have newton meters for torque. Now, there are a ton of places where these ideas are going to kick in. We are going to look at one quick example together to think out. I lied. We're going to work a bunch of examples together. So I'm going to pause this. All right, so anybody who's out on the road right meow, I will have this worksheet for you tomorrow in class, or it'll be online for you. But here's a worksheet that we're looking at. So these are just a bunch of the example problems where you can start working through these things. Here's what I'm going to leave completely up to you. If you like to have the problems in your notes, and I personally would, but I hate the writing down the questions, I don't mind if you work the actual problem in your notes as long as you have somewhere to reference that this is a question that we're answering. Okay, looking at this, I have hooked it up. We have a torque given. Notice N times M. I cannot make this less bold. I'm sorry, but I'm going to try my best to do this every time. We have a torque of 55 Newton meters that's required, and the hardest that I can push is 135 newtons. I want to know how long should the lever arm be to make this work. So if we're just jumping in immediately to the math, this problem is hopefully not a stressful one. Now, we are going to make it a point to every time go through and make sure that we list out knowns, unknowns, all that good stuff. And let's start here. So we have this. I need to be able to identify, and you need to be able to identify, what is the information that we know. And we'll kind of pop through everybody randomly. Kalisha, can you tell me anything that we know? So I love half of that. I don't want you to call it T, although I totally understand why you would. The torque tau is 55 Newton meters. So we're going to say 55 Newton meters. Cool. All right, Angel, is there anything else that we know about this particular problem? I know the force is equal to 135 newtons. Now, we're looking for the length of the lever arm. What are we actually finding? Find L. Love it. Now, if you want, we can also say L equals, and I'm going to say just question mark for now. But we could say r sine theta with one little issue. Do you know the radius of the thing that we're pushing? Ah, bummer. So we need a way around that. Okay, if only there were an equation that we could use. And there might be one more known that we're going to assume because it's not specified. If you're going to try to open this door, or whatever it is, I don't know, we're trying to apply a force, what angle would you probably choose? You probably go perpendicularly, right? If you're pushing your very hardest you can, that would be the way to minimize the amount of force you need. Is it reasonable that we can say that we know, based on the fact that we're trying to apply this and we're trying to do something, that we're allowed to use this angle? Okay, so we get theta is 90 degrees as well. Well, what's the equation for torque? FR sine theta. Now, I'm always going to wait to plug in until the very end. This year I've been kind of back and forth about whether I was going to do that. It is in your best interest to solve it without plugging numbers in every time. Okay, if I want to solve for r sine theta, there's a couple nice things that'll happen. Right off the bat, this is really L, yeah? So let's solve for that. What would you divide by first? Let's divide by force. So I know that r sine theta, and I'm going to switch sides here, or L if you will, is exactly equal to my torque divided by force. Do I have the torque? And do I have the force? And do I have theta? Okay, quick trig question. What's the sine of 90 degrees? Everybody point to where 90 degrees is on your unit circle. Straight up. Cool. What's the sine here? Try again. 1. Whoever said 0, that's okay. It's easy to get goofed up. This is 1. I probably wouldn't really write this. In this situation, the radius that we're pushing is the exact lever arm. If you're perpendicular to it, you don't have to do that fancy right triangle stuff, which means my lever arm is exactly equal to r in this case. So we'll just call it the radius. Radius equals torque over force. That's 55 Newton meters divided by 135 newtons. Anything convenient happen with my units? They gone, and we're left with something only in meters. If I ask for the length of a lever arm, does that seem reasonable?
Explain how we got to theta being 90.
So if you're going to push the very hardest that you can to open a door, you're going to push perpendicularly. Yep. Cool. 55 out of 135. 11 over 27? I don't know what that number is. Somebody's going to hook it up, though. 0.4? 0.4 what? 407. 0.407 what?
Meters.
Meters is the answer that I'm looking for, but I think I like your answer as well. Now, quiz or test, do you stop here? The length of the lever arm is 41 centimeters, or 0.4 meters if you'd rather. Cool. Super hard? Not particularly. Okay, I want you guys to spend a moment looking at number 2. I will give you a head start, but just using the things that we have here, I think you'll be okay. But let's try it out. I want you to do number 2. Talk it out with your neighbors. I will put it up here. I'm going to give you a head start before I start working on it as well, and we'll see where we wind up. Want to hear discussions? Cool. Now, Sean's question was, is the force always 90? If we have a gear, something set up like this, I see the gear's trying to turn that way. It's trying to go the positive direction right now, counterclockwise. This chain is going to act perpendicularly on this. If you can imagine that there's a bar sticking out, I'm straight perpendicular to it because a chain is always tangent to our circle, and tangents are always perpendicular to a radius. As we're looking at this problem, we do get our 90 degrees. It works out super nicely. There's one little tiny trap that I'm trying to get you to fall for that I hope you don't. What's torque measured in? The unit specifically. Newton what? Meters. And what did I give you for the radius? What might be in your best interest to do? change it into meters. Now, if you struggle to do that, just remember a century is how many years? 100. So a centimeter is a 100th of a meter. Move the decimal where? 2 to the left or 2 to the right? I guess it depends on the direction you're going, right? From centimeters to meters, we got to move it left. Because 100 centimeters, 2 to the left would make it 1 meter. Cool. I'll give you guys a little bit more time, and we'll see where we come up. So looking and checking in with a few people that I just did. Somebody hook it up. What's the equation for torque? Fr sine theta. Now, if we have a chain on a gear, it's always what theta? 90. So at this point is where I would normally do this. That's 1. Okay. The fact that I have this, I think we're just ready to like kind of cook through here. What's the force we apply? 35 newtons. And what's the radius? 0.077 in meters. And when you multiply these together, I think we get what number? 2.695. I'm going to call that 2.7 Newton meters. Now, looking at this. What's up? Theta is always 90 degrees if we have a chain acting on it, because it's always going to be tangent to our circle. So if we imagine that instead of pulling, if we imagine pushing, it's always going to be perpendicular to that radius. Anytime you're on a gear like this. Okay, last little tiny piece. I made a mistake based on this picture because I can't read. Is that what you're about to address? Yep. So just full disclosure, I can read, but I didn't read carefully. The wheel's trying to move in the clockwise direction, which means the wheel's actually going this way. My chain should have been over either going up to counter it or going down on this side. If it's going in the clockwise direction, what's it going to do? Negative. So let's see. The bicycle chain, if the chain exerts this in the clockwise direction, I'm fine with this, because if my chain is moving clockwise, then I need to move counterclockwise to stop it. Do you guys agree with that statement? Rotating clockwise, I need counterclockwise to stop it. And counterclockwise is positive or negative? Counterclockwise? Positive. Yep, I'm all cool. I'll keep it here. All right. For that, we will make sure we get a bunch of practice tomorrow when everybody's back. There is no homework tonight. Do not lose your packet. Not a packet. Problems. I don't know. You can call it a packet. Give me the friggin' packet. All right. Later, Raiders.